There's a wall in Japan so long that if you stood at one end and started walking, it would take you 4 days to reach the other, and for years, almost nobody outside Japan knew it existed until you look at what it's hiding from. Picture a concrete horizon rising higher than a 4-story building, stretching 400 kilometers along a coastline, the distance from New York to Boston and back again, twice over, every single meter of it poured, driven, and dropped into place by human hands, at a cost of $12 billion. And the reason it exists is written in the wreckage of a single Friday afternoon in March. On March 11th, 2011, at 2:46 in the afternoon. The seafloor off the coast of Tohoku did something the instruments had never fully modeled. It lurched 50 meters in under 3 minutes, a rupture so violent it displaced 500 cubic kilometers of ocean in one motion. And what came out of that motion was not a wave in any sense a surfer would recognize. It was a wall of black water 40 meters tall, moving faster than a car on the highway, and it crossed the entire width of Japan's coastline in 30 minutes. Nothing in its direct path was built to survive it. 90% of Japan's existing seawalls, structures engineers had trusted for decades, failed in that single hour. And here is the detail that haunts every coastal engineer in the country to this day. The world's largest breakwater at the time, a $1.6 billion structure at Kamaishi, celebrated as an unbreakable marvel, did not fail the way anyone expected. It didn't crack from the force hitting its face. The water climbed over the top, poured down the back where there was no armor, ate away at the foundation from behind, and the entire structure simply vanished into the sea in seconds. Proof that the enemy wasn't the wave coming in, it was the water going back out, and almost nobody had designed for that. Somewhere in the chaos of that day, one story became the blueprint for everything that followed. Decades earlier, a small fishing village called Fudai had a mayor named Kotaku Wamura who insisted, against furious local opposition, on building a floodgate and seawall 15.5 meters tall, taller than anything nearby, mocked as paranoid, wildly over budget, for a village its size. He died in 1997, never seeing the day his decision would matter. On March 11, 2011, that gate closed, that wall held, and roughly 3,000 people who should have died did not. One mayor, one wall, 3,000 lives. That is not a footnote. That is the entire argument Japan built 400 kilometers of concrete on. So the question every engineer had to answer afterward was brutal in its simplicity. How do you build something to stop an ocean? And here's what almost nobody outside Japan realizes. This new wall was never designed to stop a wave the size of 2011's. That would require structures so massive they'd bankrupt the country and block every harbor in existence. Instead, engineers built something smarter and stranger. Most of this wall you cannot see. Only about 14 meters shows above the surface. The rest is buried, anchored, engineered into ground that was tested and modeled more than 200 times in computer simulations before a single stone touched the coast. The height isn't uniform either. It climbs on exposed headlands where waves hit hardest and drops in sheltered bays every kilometer. Calibrated to its own wave data, like the coastline had been given 400 kilometers of custom-tailored armor instead of one uniform slab. 440 separate construction teams were unleashed on this project simultaneously. And here's a problem nobody talks about. If even one of those companies goes bankrupt mid-build, you don't just lose a contractor, you open a physical gap in a wall meant to hold back the ocean, so the tolerance for failure from day one was zero. Before a single machine broke ground, survey ships spent months drilling into the seabed, because the ground beneath this coastline is not one material, it's 3. Completely different problems stitched together. Soft clay in some sections, dense sand in others, solid rock elsewhere, each demanding an entirely different foundation strategy underneath the same surface wall. The first job wasn't building anything. It was demolition, tearing out the seawalls that had just failed, studying exactly how and where each one had broken, then designing the replacement to fail-proof that specific weak point. They cleared entire coastal pine forests that had stood for generations. The tide gave crews windows as short as 4 hours a day to work in the surf zone, and every single one of those minutes was accounted for like currency. In the clay sections, the ground was so unstable it couldn't even support the weight of a bulldozer, so engineers floated steel road plates across the mud to spread the load, a low-tech solution to a problem that could have stalled the entire project. And then comes the part that should stop you in your tracks. Crews were pouring foundations, 25 meters below sea level, inside the active surf zone, in the same ocean that had just erased their hometowns. Divers went down into that water, guiding 5-ton boulders into position by feel and by radio, because visibility at that depth was close to zero. Engineers on the surface couldn't see what their own foundation looked like. They had to trust sonar data completely, blind faith backed by instruments, boulder by boulder. Beneath every layer of rubble sits something almost invisible but utterly critical, a filter layer, a geotextile membrane that stops fine soil particles from bleeding out of the foundation over time. Skip it, and the wall doesn't fail today. It fails silently, year after year, until one day it simply isn't there anymore. Get the slope angle wrong by even a fraction. Too steep and the boulders slide, too flat and the waves refuse to break the way they're supposed to. And the entire physics of the wall changes. Piece by piece, a platform was rising out of nothing inside the ocean itself. Only once that foundation held did the real wall begin to climb. Steel sheet piles were driven 10 meters into the seafloor just to protect the base of the structure, interlocking in a Z profile so that force transferred evenly across every single pile. Because the wall's real enemy isn't the wave crashing in, it's the backwash, the vacuum of water retreating that can rip sand straight out from under a foundation and topple it from behind, exactly like what happened at Kameishi. One buried boulder in the wrong spot could knock a 12-meter pile sideways and destroy the entire alignment of that section, so crews learned to pre-drill and crush obstacles before ever attempting to drive a pile through. 30 dump trucks ran, 16-hour shifts without stopping, hauling fill that had to be laid in exact 300-millimeter lifts. Never more, because a compactor physically cannot reach the bottom of a thicker layer, leaving weakness buried where no one would ever see it until it was too late. Inside the body of the wall, geotextile sheets run through the fill like rebar runs through concrete, and every layer had to hit 98% compaction density or an inspector would shut the entire site down on the spot. Step onto ground. Compacted to that standard and nothing moves beneath your foot. Drop to 85% and you sink. At that pace, laying 300 millimeters a day, it would take 18 months just to reach the height needed before the next tsunami season arrived, and every single day of that clock was counted in public. At the core of the embankment sits a layer of compacted clay, acting as the wall's internal waterproofing. And when one night of heavy rain dumped 600 millimeters onto an exposed slope before it could be sealed, an entire section slumped and had to be torn out and rebuilt from scratch. A brutal lesson repeated more than once before crews learned to cover every slope in protective fabric before a single drop of rain could fall. By the time the wall reached 10 meters, thousands of precast concrete panels began arriving, and this is where the project turned almost obsessive. Sensors were embedded directly inside the structure, letting engineers monitor its breathing and settling in real time, every day, permanently. A 400-kilometer wall that reports on its own health forever. Every panel face had to be perfectly flat before installation, because a single bump can concentrate stress in one point and start a crack that spreads for years. Each 7-ton panel served 3 separate engineering functions at once. Gripping the seabed, sealing against water intrusion, and carrying structural load, 3 jobs compressed into one slab of concrete. If a panel cracked inside its mold, it didn't just cost material, it wiped out an entire week's production schedule, and inspectors would physically tap finished panels listening for the sound. A solid ring meant the concrete had cured correctly, a hollow sound meant an $800 panel got crushed on the spot. No exceptions, no negotiation, because there is zero tolerance for defects on a wall meant to survive a tsunami. Moving 7-ton slabs down narrow coastal roads required flagmen, posted at every junction across the entire 400-kilometer stretch, and the foundation bed beneath each one had to be level to within 5 millimeters. A bump barely visible to the eye could crack the corner of a concrete panel engineered to take a wave impact at 30 kilometers an hour and hold for a century. Along curved sections of coastline, straight panels would leave 20-millimeter gaps for water to force through and undermine everything beneath. So engineers designed 37 unique panel shapes, each one CNC machined to close every gap to zero, an entire custom-built jigsaw puzzle wrapped around a coastline that refused to be straight. The joints themselves used rubber water stops that swell when wet, meaning the bigger the wave, the tighter. Every seal becomes a wall that literally reinforces itself under pressure. And through all of this, a 2022 deadline loomed over 440 teams racing in parallel, every one of them building toward the same finish line at the same time. At the very top, the crown wall's nose curves at exactly 10 degrees from vertical, a single angle that throws overtopping water back out to sea instead of letting it crash down onto everything behind. One detail, invisible to any tourist walking past, quietly protecting thousands of people. From a distance, this wall looks like a slab of gray concrete. It is not. It's 6 different materials performing 6 different engineering functions simultaneously, because the engineers learned the hard lesson of 2011 permanently. The back of a wall matters as much as the front, because that's where the old ones died. If water does eventually top the structure, it needs somewhere safe to go, which is why a landward drainage system runs the length of the wall like a nervous system, an engineered escape route for water that was never supposed to be there in the first place, and then past the wall itself into the water. 32-ton concrete tetrapods, strange four-legged shapes that aren't placed with precision at all. They're simply dropped, left to find their own stable position. Chaos producing order, one leg always pointing upward to catch the tetrapod above it, interlocking into an armor layer that absorbs wave energy on impact. The gaps between them aren't a flaw, they're the entire mechanism. Water flows through those gaps and loses its energy, dissipating through them instead of slamming the wall directly, 1 liter absorbed at a time. And then you multiply that by 50 million tons of moving ocean, and you start to understand the scale of what these structures are actually fighting. There's a real equation behind all of it, the van der Meer formula, translating wave energy directly into a minimum required armor weight. And crews were placing 40 of these tetrapods a day, a yard running around the clock that never stopped, because 400 kilometers of coastline needed armoring, and the sea does not wait for anyone's schedule. Below the waterline, sonar-mapped tetrapods no diver could safely reach, forming 3 separate defensive lines before the wall ever takes a direct hit. Rubble mound, sheet pile tow, tetrapod armor, designed so the tsunami exhausts a portion of its own force before it ever reaches the structure people actually live behind. But concrete and stone were never going to be enough on their own, because 400 kilometers of wall still needs 443 gaps. River mouths, harbor entrances, roads, and every single one of those gaps is a potential death trap if even one floodgate fails to close in time. Those floodgates are built with concrete twice as thick as anything else on the wall, because this is precisely where tsunami force concentrates hardest, funneled and multiplied through a narrow opening. From the moment a seismic sensor detects an earthquake to the moment the gate must be fully sealed, engineers had exactly 70 seconds. No human decision required, no phone call, no committee. The ground shaking is the trigger, and the gate begins closing on its own. Picture a 22-meter steel curtain stored open at the top of its frame, held there only by mechanical release. When triggered, gravity alone pulls it down, meaning even if every generator in the region fails, even if the power grid goes completely dark, the gate still closes because it was never depending on electricity to fall, only to hold itself open. Engineers machined tolerances down to 15 millimeters on 50 tons of moving steel, tested under 1.5 times the pressure the design was rated for, because if even one of 14 separate seals leaked, the entire gate would fail its purpose. And when a test revealed 40 liters per minute slipping through a 2 millimeter gap, knowing that gap could widen to 20 millimeters under real tsunami pressure, they didn't patch it. They machined it down further, retested, and only accepted 0 leaks, 3 additional hours of precision work that could be the difference between a town surviving and a town gone. All 440. 3 of these gates report to a single command room, monitored by one integrated system tracking every gate, every sensor, every alarm along the entire 400-kilometer length simultaneously. A wall that, in a very real sense, thinks for itself. Every March 11th, without fail, Japan runs a full drill of this entire system, because memory fades but the ocean does not. On the sections where cliffs replace beaches, there's no foundation to dig at all. Engineers bolted the wall directly into solid rock, drilling 2 meters into basalt, spraying concrete at speeds over 100 kilometers an hour so it bonds into the stone itself rather than simply sitting on top of it, fusing 3 separate materials, rock, spray concrete, and steel, into one continuous, unbroken face. Offshore, submerged breakwaters trip incoming waves 200 meters before they ever reach the main wall, forcing them to break early and lose power before the real fight even begins. And rebuilding Kamaishi's breakwater, the very structure that had failed so completely in 2011, meant sinking a 60,000-ton concrete box to a depth of 63 meters, an operation that nearly went wrong in real time when the towing tug lost steerage and 30-knot winds, and that 60,000-ton mass drifted 8 meters off its intended mark before crews wrestled it back into position. Proof that even with 200 computer simulations behind you, the ocean still gets a vote. The rebuilt structure now stands stronger than the world record it replaced. A philosophy stamped into every decision made after 2011. Never rebuild the same thing, always build back stronger. Quality control on this project bordered on obsessive by design. Any panel that failed a strength test was sent straight to the crusher, regardless of cost or schedule pressure, because 2 millimeters of carbonation on a concrete surface determines whether the steel reinforcement inside stays untouched by corrosive sea air for the next 100 years, and an independent inspector held the authority to halt any section and order it demolished. No appeal. 440 contractors operating permanently under that pressure. And then, in the middle of construction, the real test arrived without warning. A 7.4 magnitude earthquake struck the coast. Seismic sensors fired instantly, All 443 floodgates began closing simultaneously, exactly as designed, with no human hand guiding a single one of them. When engineers inspected the wall afterward, they found 0 cracks and 0 shifted tetrapods, a result so far beyond what anyone expected that it stands today as one of the most extraordinary validations of coastal engineering in modern history. Not a simulation, not a model, a real earthquake, and the wall simply held. Today, a helicopter can fly the full 400 kilometers of this structure in a single pass. And what that footage reveals isn't only concrete and steel, it's staircases built directly into the wall, not for tourists, but engineered from crowd flow science as emergency evacuation routes, pathways designed to move an entire town to safety in minutes rather than hours. And in the years since completion, something almost nobody predicted has happened. People walk their dogs along the top of this wall. They run in the mornings. They cycle for kilometers along a structure originally conceived purely as defense against annihilation. It has quietly become something else entirely. A daily promenade, a shared spine along the coastline, a place where the same communities that watch the ocean, take everything from them in half an hour now, walk every single day, atop 400 kilometers of concrete, steel, and grief, built one boulder, one panel, and one impossible decision at a time.